today we're going to finish up section 2.2. It's lecture 13, class 13. It's on something called piecewise functions. And there is a change in the schedule, so please note it. When I did this schedule again, I put the quiz in the wrong spot. The quiz, our quiz 2 should be Wednesday, the same day we do linear regression. So I will take one of the classes off. It won't be classes 9, 10, 12 through 14. Notice it will just be 9, 10, 12, 13. So that quiz will be Wednesday, the 5th, March 5th. So just scoot it up with an arrow one day, okay? So the quiz will be on Wednesday, the 5th. This quiz will be on this day, so put it up in there, okay? So when you come in, please look at whatever's in the top. This because you need to pick it up. Did anybody not pick up their lecture notes when they came in? Okay. All right, so quiz next Wednesday, not Friday. And just in case, if there's a snow day on Monday, it couldn't have fallen on a better day, because if you look at this packet that I just gave to you, class 14 is supposed to be Monday. It's all review. It's all on slopes of lines, how to make equations for lines. It's all line material. So Monday, my plan was to just have you start on class 14 on your own, and I was just going to circulate and help people as needed. So I wasn't even going to lecture on it. So this is the part I need you to listen to carefully. If for some reason there's a snow day on Monday, I have 2 videos from fall 13 that covers all of the material for our class 14. Some of it may not be in exactly the same order, but it's there. For example, on class 14, the first page, these last 2 graphs, they're later on in the lecture. So everything in class 14 is covered by those 2 videos. It's just not necessarily in exactly the same order. So just be patient. If they're starting to talk about something that's not on your page, just turn the page. You'll eventually find it, but it's mainly the same order. Okay. Now, you are to cover this on your own Monday if we have a snow day, and do your homework Monday for Wednesday. Again, it's a review. If it had been really new material, like if it had been today's lecture, I wouldn't have asked you to do it. Okay, because it would have been too rough for you to handle. All right. So again, if you came in late, we're having the quiz on Wednesday next week and not Friday, and it will only cover to class 13. Any questions on that? Anybody have any questions? Okay, so let's get going. Piecewise functions. Today's class number is right here, Dan. Lucky 13. So you're on, that's a handout for next week, Dan. Do you have today's lecture notes with you? Okay, would you hold this down for me? Don't want to scare anybody. All right, so when it comes for us, okay, so let's jump right in and see what all this means. Why is it that sometimes we might have situations like taxi fares or federal tax codes? I just did my taxes last night, so I understand how that works. That needs 2 pieces of the domain, or 2 different, or maybe sometimes 3 or 4. I mean, it could require a variety of pieces. So let's take a look at one that hopefully we can be familiar with. Now, I'm sorry that this little box got put right in the middle of the graph. On your paper, it's over here where y equals f of x, covering that. So let's take a look at this graph. The graph below represents a piecewise function. Now, first of all, when you look at a graph, how do you know it's a piecewise function? Well, if you can't represent the picture with just one equation, then you know it's got to be represented by different pieces. So if you look at this, right here, the first part of the graph is a increasing straight line. It's a line segment right now. The next part is a constant, and then the last part is a decreasing line. So there's no one formula that's going to capture that whole picture. So this is one way you can quickly tell that a graph is a piecewise function. Okay, so what's happening in this graph? This graph shows the amount of water in thousands of gallons, that's our unit, in a swimming pool after T hours have elapsed. So the first question here is, how has the pool, water in the pool changed over the interval? T equals less than or equal to 50,000 gallons, greater than or equal to 0 gallons. And remember, when we talk about intervals, in this particular case, it's always over our independent variable. Our independent variable here is time, the number of hours that has elapsed. So could someone tell me the story that this graph is telling us using the variables and the units here? What's happening? Chris? The water in the swimming pool increased steadily, yep, for 20 hours until, well, you're assuming full. What does full mean in this picture? Well, what is full? How do you, what are you defining as full? 8,000 gallons, okay. Can't write that fast. And remained at 8,000 gallons for what? For 10 hours, yeah. And then decreased steadily for 20 hours until empty. Good. I had a fun time in my first class when one of my students defined it, told the story. So the language was very interesting. Okay. So the water in the swimming pool increased steadily for 20 hours. Where did the water start, Chris? Right, so initially, I'm just going to do a little addition here. Initially, the pool had 2,000 gallons of water in it. Okay, and then the water in the swimming pool. Now this is very interesting, this word that Chris used in two places, increase steadily and decrease steadily. Why did he use the word increase? Well, we can see why he used increase, because the line is moving upward as we move from left to right. Why did he use the word steadily? Right, it does, the rate that the swimming pool is filling up is constant. And the word steadily represents that. So this pool is filling up at a constant rate. That's why that line is straight. That's what makes the line straight, is there's a constant rate of change between whatever two variables you're looking at. And similarly, it's decreasing at a steady rate. Sometimes things might fill up more quickly and then slow down, right? That would be more like a curve. But in this case, Chris used the appropriate word steadily. Okay. So yep, this swimming pool is filling up, then it's hanging out for a while at 8,000 gallons, and then it starts to drain out. All right? So that's great. Over what interval is the water in the pool increasing? This is just a little review from Monday's class. At what interval is the water in the pool increasing? I heard 0, 20. Is that how you would represent it on your quiz next week? No. Parentheses, because it's always an open interval. Over what interval is the water level constant? Jonah, just go ahead. And over what interval is the water decreasing? Parentheses 30, comma 50, parentheses. Okay. So these three intervals helps to define the domain for this function, for this piecewise function. So I've gone ahead now and I've shown you how we represent piecewise functions. And to many of you, this may be new notation, so I'll try to cover it slowly here. So we can represent the pool problem by writing the number of gallons, G, capital G, as a function of the time that's elapsed. So we say G of T. Okay? Notice now we're using a big capital letter G instead of those little F's that we've been using all along. Notice how we always, when we represent a function, it's an equation, so you always have an equal sign. This always has to be there because you're representing a function. For some reason, and I don't know why it happens with piecewise functions, but every single semester I'll ask for the piecewise function. People do this, they say, students do this, G of T, they totally leave out the parentheses and then they just put the braces. There's like no equations at all. So you may want to circle that on your paper and just put a little asterisk or something to remember to include your equal sign. Because remember, you're trying to say what the actual number of gallons are based on some expression on the right-hand side. So notice we've got three expressions on the right-hand side. We're saying that if the time is less than or equal to 20 hours and greater than or equal to 0 hours, this is how we figure out how much is in our pool. We take T, we multiply it by 0.3, and we add 2 to it. So if I wanted to know what G of 10 was, I have to find my appropriate domain. 10 is right here. 10 is between 0 and 20. So I would use this formula, 0.3 times 10 plus 2, which is 5. So after 10 hours, there's 5,000 gallons of water in that pool. Okay. Now, once I get up to 20 and I'm between 20 and 30, my water level doesn't change. And that's why you just see this equation right here, which is a constant, G of T. So if I'm 25 hours in, G of T, G of 25 is just 8. It's constant. It doesn't change. Notice my first little expression here changed steadily. It increased. It's the slopes right here. I have 300 gallons per hour. That's what point T means when you're looking at thousands of gallons. 300 gallons for every hour that goes by, plus 2, because that's where I started at 2,000. Okay. Then, how would I represent this last domain? So here's my first part of my domain between 0 and 20, then 20 to 30. And how, looking at my notation here, how would you write the last piece of the domain there? What would you do? Any guesses? 30 to where? I think, let's see, this was, for some reason on mine, my domain didn't come out. Let's see, 0, 10, 20. Is it on your paper? I hope it came out on your paper. Okay, so what's this last point here, Amy? 50, I think, isn't it? Is it 50? Okay, so we got the 30 there and we got the 50 there. Now, how do we write the inequality? $30 is less than T, notice, and then T is less than or equal to 50. Okay. Now this was arbitrary, folks. I could have done this. I could have defined it like all of my domains like this. Look, I could have made my endpoint on my first domain right here open with no equal sign, and then I would have included it at the beginning of every one like this. You see, I could have just done it this way. So see here, these two are open at those points, and here I've I've put it at the end. It doesn't matter, just be consistent. So if you say at the end of your first interval, you're going to include 20, then down here, have it be not included. If you include 20 here, you're going to include 30 here, and then you would open it here and then include 50 as your last point. Okay? And this, so listen carefully, in this particular picture, it doesn't really matter a whole lot whether you put less than or equal here or here, because look, what do you get if you put 20 into this first line? 0.3 times 20 is the number 6. 6 plus 2 is 8. What happens if you include 20 here? What's your answer? 8. Because that point is on both of these lines. 28 is on this first line and 28 is on that constant line. It's only when you get your piecewise functions where the graph jumps, there's a big gap at a point, that you got to be really careful whether you have your equal to sign on your endpoints. Okay, so you'll see one in a minute where it jumps. Okay, but right now this is, you could trace this with your pen, right? And without ever picking it up off your paper, you could trace this whole thing from t equals 2 to t equals 50. So this is piecewise notation. We have 3 separate graphs. We have 3 separate pieces to our equation. Any questions on this before I go on? Anything at all? Now, in my first class, someone said, why is that number there 20 and not 8? Why is that 20 and not 8? So someone else said, oh yeah, I was wondering the same thing. Is anybody wondering that here? Right, so notice that right now we're only looking at, if I asked you to graph this equation over the domain of all real numbers, it's going to be a straight line with a decreasing slope, not a line segment like we have in this picture. So if you actually graphed this entire line, if you graphed y equals negative 0.4 t plus 20 over all real numbers, then this thing is going to continue at the same rate forever and ever in both directions. And if you think about this line continuing up, what this says is it's going to hit my y-intercept at 0.20. So, and in fact, all you have to do is put t equals 0 in here. That goes away, and there's your 20. Okay. So, okay. That was just a question that came up in the first class. I thought it was an interesting question, so I thought I'd share it. Okay. So you get the benefit of all the questions from the first class, too. All right, so this is a true story. Well, until this month, last month, I never went over my 700 minutes. But this is what my plan charges. I have 700 minutes on my Verizon wireless plan, $79 a month for 700 minutes. And any minute I go over 700, I get charged 45 cents a minute. So last month, thank goodness it was only 701 minutes. And so I got an extra little charge tacked on to what I think is outrageous prices anyway. So I want to use a piecewise function to represent the monthly cost of my cell phone using a piecewise function where C is the monthly cost in dollars and M is the number of monthly minutes used. Can anybody help me identify my independent and dependent variable? In other words, one of my variables is my vertical variable and one of them is my horizontal. Can anybody help me here from either looking at the notation I already have written down or from the story? Yeah, Gina? All right, so the dependent variable is the cost, monthly cost in dollars, yep. And the independent variable is the number of minutes. Yep, monthly minutes, right? Number of monthly minutes used. All right, so we know where each of those variables are going on my graph. And how many pieces do I need to graph this picture or this story? How many different pieces? Yep, 2. And how would we just plainly talk about those 2 pieces? Why 2 pieces? Yep. Right, because I'm going to have one cost. I'll have one cost if I use M less than or equal to 700, right? And greater than or equal to 0 minutes. So anywhere between 0 minutes and 700, I have a cost. I know what it's going to be. It's $79. And then what's the other situation, Cooper? No, just the other situation. I don't care about what the graph looks like. Just what's the one situation is where I have one cost if I talk for. So if I talk for more than 700 minutes, I have another cost, right? Another cost. All right. All right. I'm going to do the first part for you. All right. So I'm going to do my charge is $79, comma, if, what's the condition I place on that? If I talk for less than or equal to 700 minutes or more than or equal to 0 minutes. So if I talk, if my number of minutes is in my range that the plan allows, 700 minutes, my cost is $79. What I'd like you all to do is to fill out the next part. What if you talk for more than 700 minutes? So if M is greater than 700, figure out what would go in that box. It's not straight necessarily very simple or straightforward, and it takes some thinking, but that's okay. We'll get there. Okay. I think most of you got there. So let me try to help you whenever you have a situation like this that you can't quite figure out with the algebra. This is a strategy I used throughout my lifetime. Use arithmetic, because you know how to capture this if I give you a specific value for the number of minutes you talk. For example, off on the side of your paper, you can say, you can call this your ThinkPad. I know that IBM uses that for a computer, but this is going to be your ThinkPad. And you can say, suppose I talked for 800 minutes. Tell me every step of the process you would go through to figure out your monthly cost. What would you do? .45 times 800? Well, M is 800. So I'm going to make believe we talked for 800 minutes. So how would you figure out your cost? Is it 45 cents for 800 minutes? After this, yeah, 79 plus. This is going to be the cost right here, $79. And then, so I'm going to get charged 45 cents for all 800 minutes? No. I'm not going to get charged 45 cents for all 800 minutes. That would be no, what do I put in here? Okay, so I don't put the 800 in there. But what do I put in there? How many minutes am I going to get charged for 45 cents a minute? 100, right? Because that's over, 800 is 100 minutes over 700. So to figure that out in a formula that works all the time, you put the number of minutes you talked in there minus your 700, which is your base number, right? That's what your plan allows. So the cost is going to be $79 plus 0.45 times 100 minutes, because that's how many minutes you've talked over 700, right? And that's how you get the overage, is you subtract 700 from 800. So in general, for any number of minutes over 700, you now replace your 800 with the variable M. So if you talked for 900 minutes, then it would be 0.45 times 200. Okay? So that's what goes right here, $79, which is your base cost. And then this next cost is your overage charge when you go over your minutes, 0.45 times M I should have made my box a little teeny bit bigger. The number of minutes minus 700. Okay? But remember, Brittany, 45 is just a rate. It's 45 cents for every minute. So there has to be some number of minutes after it, because in order to add it to 79, which is just dollars, this has to represent a dollar amount. So you got to have the number of minutes after it. No, you can leave it just like that, because that tells me what's going on. Okay, so what's the rest of it? The rest of this problem now asks you to interpret. So if I gave you a function like this on your test, a piecewise function, and I said, find C of, what is it, 525 or 535? 535. So if right underneath I said find C of 535, you have to know that 535 represents the number of minutes. That's your input. And then you have to go to the appropriate equation, the appropriate formula. 535 is on your first domain here, right? 535 is defined right in there. It's between 0 and 700. So the cost will be 79 bucks, right? And then what's the next one? C of what? 850? Okay. So now you say, what formula, what piece is going to define my cost? So first find the domain where your cost is included. Now in this particular case, 835 is bigger than 700. So this is the formula that you use to calculate your cost. 79 plus 0.45 times 850 minus 700, which is $79 plus 45 cents a minute for the 150 minutes I went over. And does anybody have this done? 45, well, it's 67.50. So my total cost then is 146.50, right? So the cost for 850 minutes is $146.50. Okay? Any questions on that? So this takes a little while, but once you see this once, then you'll recognize it in other applications that involve overage charges, when you go over something. Okay, which there's quite a few of those actually. Okay, we've done that. Okay, so now this is this is just what I call, this doesn't have any story to it, right? This is a piecewise function. It's defined in two parts. It says if you're less than 1, so your domain is less than 1, what kind of picture are you going to be? What kind of equation is that? F of x equals x squared. What kind of equation, first of all? It's an even, yeah, it's an even function. X squared is an even function. But what kind of equation is y equals x squared? What'd you say? I couldn't hear him really because I got this sound. Not exponential, x squared, second degree equations. What are those called? Quadratic, right? And what's a picture of a quadratic? What's the graph of a quadratic look like? Parabola, right? So when you're less than 1, you're going to be some kind of picture that looks like a quadratic. Then when you are bigger than 1, what kind of picture is that? Y equals 1 minus x squared. Linear equation in two variables, which is a straight line. So one of the best things I liked about this book, this is what kind of got me into my math lab, is I want to show you, just watch for now, and then we can do it together. It's going to be exactly the same problem on this video here. And I really thought this was like one of the coolest ways of showing, oh, no, I don't want you, just, where'd I put it? Should be here. I had it already. I'm waiting for you. Come on, where'd it go? Oh, maybe it's in Chrome. Yeah, it is. Thank you. Okay, so here it is. You're going to see a video of how to sketch that piecewise, but it's really cool what the guy does. We will sketch the graphs of each equation independently. We start by sketching the basic function y equals x squared. However, we are only interested in sketching this graph for values of x that are less than 1.
We must therefore eliminate or erase the portion of the graph for values of x greater than or equal to 1. Note that the point 1, 1 is not included on this graph. We can sketch the line y 1 minus x by first plotting the y-intercept of 1, then using the slope of negative 1 to find another point on the graph. Since we are only interested in the portion of the graph for values of x greater than or equal to 1, we must eliminate the portion of the graph for values of x less than 1. Note that this graph contains the point 1, 0.
What do you think about that? Yeah, I thought that, I mean, that was like the coolest way I've ever seen someone explain how to draw a piecewise function. So if you think about it, exactly what he did is he drew the original function as if you had the whole real number line as your domain, and then he just erased what we're not interested in. Now, right here, this is the interesting part right here. Right at 1, because 1 isn't defined on this domain, is it? So you can't use the value you get from your quadratic x squared. 1 is defined on this domain where we're looking at this straight line. So notice if I drew a vertical line right down through x equals 1, I couldn't go through 2 points or else I wouldn't be a function anymore. So one of those values has to be an open circle and one of them has to be a solid. Okay? So any questions on that? Any questions? Okay, you try drawing it at your seat. So, okay, so we have the graph from our animation, and all of you that I could see successfully were able to draw it. And now you could either use the graph, if you were lucky enough on either a homework question or an assessment, you might have both the picture and the algebraic representation. F of -3, first of all, you have to figure out which domain is -3 on. And you go up here and you say, well, -3 is less than 1. So this is the formula I'm going to use. So f of -3 is -3 squared, which is 9. Then same thing here. F of 0, 0 is less than 1 too. And I can either look right on my graph and see my answer is also 0, or I could use my formula and get 0. 1, that's, oops, I drew my line wrong. Shh. At 1, that's the tricky spot. Here's my line. Like that. Okay. So at 1, you say, okay, 1 is not less than 1, but 1 is equal to 1. So you're going to use your second formula and throw 1 in for x, and you also get 0. That's the point right there, 1, 0. And then 10 is bigger than or equal to 1. So you use the second formula and you put 10 in, and there's your answer, -9. Any questions on that part? All right, now this next function is a little weird at first to get used to. Okay, and the graph of it's a little strange, but we'll be working with this. Your third project will work with this. The greatest integer function is one of your functions. We're going to call this a parent function. You'll know what that means in a while. But this is like one of what is a basic function that when you come out of a college algebra class, you should at least have some idea in your head, some visual for. And it has a very interesting symbol. It has a symbol that looks like brackets, but notice it has like a double vertical line here, right? So when you see this symbol, just like you've learned the absolute value, which is just 2 vertical lines means absolute value, this stands for the greatest integer, less than or equal to whatever number is in between those 2 symbols. It's the greatest integer. So the first thing you got to know is, what the heck do the integers look like? Here are your integers, all the numbers you always think about. all your whole numbers, and then their opposites. Those are your integers. So here's your integers. Okay, integers. So you'll see that symbol. Your book uses this, int, parentheses x. So the greatest integer x, the greatest integer less than or equal to x. So now, when you see this, and you're asked to define it, it might help you to visualize where that is on the number line. The number there is 2. What's the greatest integer less than 2 or equal to 2? 2. Okay, there we're done. We're done. Okay, now let's do the next one. That funny symbol, 2.6. So let's visualize where that is on the number line. And now I'm asking, what's the greatest integer less than or equal to 2.6? So what's the integer that comes before 2.6? 2, right, you got to go backwards. So that's 2. Right. What about the greatest integer of 2.9, which is right there? That means the greatest integer less than or equal to 2.9. 2. What about 2.99999? What's the greatest integer less than or equal to 2.999? 2. All right. So if you're on the domain between 2 and 3, your output is always 2. Let's skip now. Let's go up to 3. Okay, so here we are at 3. The answer here is 3. The greatest integer less than or equal to 3 is 3. Now 3.6. What's the greatest integer less than or equal to 3? 0.6. 3. 3.9. 3. Okay. Any number between 3, including 3, and up to 4, but not including 4, if you put it into the greatest integer function, it will spit out a 3. Okay. So notice how we jump from 2 to 3 in the function. Okay, so if you're on the interval, if your number is between 2 and 3, including 2, then the greatest integer, the value for the greatest integer function of x is 2. If you're a number between 2 and 3, including the 3, and you put it into the greatest integer function, it spits out a 3. Okay, so let's try this one. What is the greatest integer less than or equal to negative 2.3? When you're on the negative side, this really helps to have the number line. So let's throw in our number line here. Okay, so let's put in negative 2.3. All right, oops, I didn't even write that right. Let's see. This always happens when I hurry. So don't hurry on tests. Negative 3, negative 4. Okay, so let's put in negative 2.3. We'll just say there's negative 2.3. And this is the part you got to be really careful of. What is the greatest integer less than negative 2.3 or equal to negative 2.3? Negative 3, because remember, you get smaller when you go to the left. So that answer is negative 3. And what about if I put in negative 0.3? What would my answer be? Negative 1, right? Okay, so here's the fun part, is the graph. Let's graph this function. The first thing you're going to notice is the left-hand side. So I've just recopied the definition up here so you remember, okay? Notice when you write the table for the greatest integer function, you don't have a single value in here for x anymore because you're defining it over an infinite domain between two numbers. So let's start with maybe where we began this whole exercise. We started right here on this line. Let me highlight it. When we started this, we started with numbers 2, 2.3, 2.9. So we were right in here. So the greatest integer function for any number between 2 and 3, including the number 2, is what? What would be the output value if I'm an x anywhere on that interval? 2, right. That's the greatest integer less than or equal. So I go over here to 2. I go up to 2 and I put a closed circle because 2, 2 is defined. And I do a solid line all the way over to 3. But what happens at 3? What do I put at 3? Is my value 3, 2? No. Right? My value at 3, the greatest integer function for 3 is equal to 3. So you got to jump up to 3 like that. And then you go over to 4, and you're still defined to be 3 until you get to 4, and then you jump up and you're 4. So this is like a leapfrog all the way along the x-axis. So we got a 3 here. What about this interval from 1 to 2? And that's we take any number between on that interval, and we ask what the greatest integer is. What would the output be? What I put right here in the y column, or the f of x column. 1. Okay, so that means at 1 I have 1, and I'm 1 all the way over to 2 when I hop up and become 2. Same thing with 0 to 1. Negative 1 to 0 is negative 1. Okay, all the way out like that. Okay, same format. This is a graph of f of x equals the greatest integer of x, and either way you want to write it with either symbol. Okay. So it's a little different graph. It has lots of jumps and holes in it. Okay. All right, so now what you have before you is 5, 10, 15, 17 minutes of group activities. There's 4 of them. They get more and more challenging as you work through them. I have in my possession an answer key. I have an answer key for those 4 problems. When you have made a really good effort, even if it's not right, to try all 4 problems, I will give you the answer key. Okay? So you can ask me anytime for it, but I'm going to ask to see your 4 problems before I give it to you, because I don't want you to, like, I don't want to steal the glory of you figuring it out on your own, okay? So have fun. They're fun problems. They'll bring up some answers, some questions, and hopefully some answers as well.